In this short video, we're going to start talking about electric fields. In another video, we've been covering actual forces on particles, on charged particles, but this we're going to talk about the relationship between those forces and the actual electric field. So hopefully many of you will already know this, but an electric field is actually the agent that exerts an electric force on some charged particle. And this is really the way that we're going to be thinking about electric fields in general. If I have some ambient field that exists everywhere throughout the universe, which is true, the value of the field exists at every point in space, then I can imagine just putting down a little charged particle, and how that charged particle responds to the way that to the electric field tells me about the electric field. So let's formalize that a little bit more. Just a couple of little things. Electric fields are created by other charges. Okay, so this is something where we've seen, and we'll see it again shortly, that if I have a charge sitting there in space, and this exerts a force on another charge, okay, and this force is mediated by the electric field, and we'll draw electric fields in various ways shortly as well. Electric fields, as I mentioned, exist in all points in space. And finally, the electric field at some point in space is given by the symbol E. This is, of course, a vector. Electric fields have directions as well as magnitudes. And if I have some electric field E at a point in space, then a particle of charge Q, little q, feels a force F equals Q times E. Okay, so let's see how that works by calculating the electric field of just a single point charge. So we now want to consider the electric field around a point charge. And we, of course, know how to do this now. We have all of the ingredients that we require. So the game that we play is we basically consider some test charge Q that's near some larger point charge, big Q, okay? And so we have some charge, big Q, okay? And if this is positively charged, then one thing that we can do is we can draw field lines. These are our electric field lines. And these, for a point charge, for a positive point charge, these go radially outwards. If this was a negative point charge, then they would come radially inwards. And this is basically how we draw our field lines. We're going to draw much more complicated configurations of field lines as we go through the course. But these become a very important tool to enable you to visualize what electric fields actually look like. So to take an example, one thing that we'll derive in just a second is we'll show that the electric field, the value of the electric field from a point charge falls off as 1 on the distance squared, okay? And so one thing that you can see here is that if I was to draw a little box around at some distance away from my charge, then, for example, if I draw a box out here, then it would have one field line going through it. Whereas as I move closer, you can see that the density of field lines actually increases. And because the density of field lines increases, or in other words, the number of field lines that pass through my box increases, this is actually a representative of saying that the actual strength of the electric field increases as well. So when you draw these field lines, and you have to be a little bit careful about the way in which you do this, but just for a simple system like this, when you draw these electric field lines, then you can see that the density of field lines in any given region of space is representative of how strong the field is, okay? So we can actually calculate how strong the field is for our point charge, and we've got all of the ingredients to be able to do this now. If you recall that the force on a point charge, so what we're going to do is we've got our point charge, big Q, and what we're going to do is we're going to put down a little point charge, and we're going to say that this little we'll call this the test charge. Our little test charge has a value of little q, and it's sitting somewhere in space near our point charge, big Q. And what we can do is we can calculate the force on little q, okay, caused by big Q. So the force on little q caused by big Q, this is a vector. This is equal to, if you recall, 1 on 4 pi times epsilon naught. Bearing in mind we've been switching between epsilon naught and k here, which we'll do a little bit throughout the course for the strict definitions, and I encourage you to look at the textbook, but epsilon naught, k is simply equal to 1 on 4 pi times epsilon naught. So the force on little q is 1 on 4 pi times epsilon naught multiplied by the value of the big charge, the point charge, multiplied by the value of the test charge, little q, divided by the distance between them squared. You remember the force between these two objects falls off like the distance squared. And then because this is a vector, I need this to operate in some direction, and this acts in the radial direction, okay? And you can see that because, of course, the force on this particle, if these are the same sign, then the force would be trying to push this away, which is simply in the radial direction. So this is the force on charge Q. If you remember from the previous slide, we wrote down that the electric field can simply be written as a function of the force, and so the electric field is simply the force divided by the value of the test charge. And this is actually the purpose of having a test charge, is that my test charge is the thing that feels the force, and once I feel that force, once I can calculate the force on a given test charge, I can then calculate the value of the electric field. So I can turn the crank. This is simply this guy, 1 on 4 pi epsilon naught, Q on r squared, divided by little q. So I get that the value of the electric field is 1 on 4 pi epsilon naught times big Q. My little q's cancel, little q divided by little q, divided by r squared. And again, this is operating in the direction of little r. This is a unit vector in the r direction. And this makes sense, okay? Your electric field is going radially outwards, which is exactly what this is saying. The value of my electric field, or the direction of my electric field, is in the unit vector in the radial direction, so it's moving so it's pointing radially outwards. Of course, radially outwards is capital R. If this was a negative charge, so if this was charged minus Q, then of course you would see there would be a minus sign in here, which would turn the direction of that vector around, and so I would get my vectors pointing inwards, my electric field line pointing inwards. The other thing that I want to point out, two more things. One is you can no longer see the value of the electric test charge in here. So the value of my electric field is completely independent of the test charge, okay? And this makes sense. I'm saying that my big Q is generating some charge. It's generating some electric field, sorry. My big Q is generating some electric field. What is the value of that electric field everywhere in space? Well, it's independent of what kind of charge I put in there. Of course, when I put a charge in there, the force that that charge feels because of this electric field absolutely depends on the strength of this charge. The other thing that I want to point out is that this falls off like 1 on r squared. So the electric field falls off like 1 on r squared. You can imagine a universe in which there is only a single charge, okay, a single charge of value Q. Then this actually causes an electric field everywhere throughout the universe, okay? And at least formally, the value of that electric field falls off like 1 on r squared, and so the value of the electric field doesn't reach 0 until I'm infinitely far away from that value of the electric charge. Here endeth the lesson.